The news came in back in May. MOND was dead. Cassini had killed it. MOND, or Modified Newtonian Dynamics, is an alternative theory of gravity originally intended to explain why the outer reaches of galaxies rotate far too quickly given their apparent mass from luminous stars. A typical spiral galaxy such as our own, the Milky Way, has a lot of stars near the center and fewer towards the edges. If the mass of the galaxy decreases as you go out from the center, then the outer stars should rotate around the core, much like the planets of our solar system orbit the Sun, where mass is also concentrated at the center. Planets closer in orbit the Sun very quickly, while those further out orbit more slowly. In fact, the orbital velocity of Mercury is nearly 10x that of Neptune. Our intuition from the solar system should scale up to galaxies if Newton's law of gravity applies at the galactic scale the same way it does at the solar scale. But when astrophysicists observe the speed of stars in ours or other galaxies, they find that it does not. Rather than modify Newton's laws, astrophysicists proposed that an invisible kind of matter was filling up the space in galaxies with a uniform kind of dust. This dust is so uniform that the mass density of those galaxies doesn't fall off until you get well past the stars at the outer edges. Because the galaxies are about as dense in the outer parts as in the middle, stars tend to feel the same pull of gravity no matter how far they are from the center. This model worked okay, but not that great. Why didn't astrophysicists decide that Newton's laws were broken and come up with something new? Partly it was because changing the theory of gravity would have a lot of other consequences. For example, those laws work extremely well in the solar system. What alternative theory would change Newton's laws at the galactic scale but not the solar system scale? There is, however, a more compelling reason to believe in dark matter. As scientists observed the universe more and more, they found evidence of it at larger scales. Einstein's theory of general relativity says that matter can cause light to deviate from a straight line course. It bends much like how light bends when traveling from air into water, which causes strange effects like making a pencil placed into a cup look broken. Galaxies warped light around themselves as if they had far more mass than is visible. Clusters of galaxies warped light as if the matter we could see was not where the greatest concentrations were. Even at the scale of the universe, we could observe dark matter. The universe could not, based on our best understanding of cosmology, the study of the universe as a whole, have formed the way it did without dark matter. We can see the signature of dark matter in the distribution of the cosmic microwave background radiation, the earliest light we can see. To explain all of this with an alternative theory of gravity seems like a stretch, and yet people tried to do so. The problem came down to those pesky galaxies. The dark matter theory simply did not work that well, not nearly as well as it did at the scales of groups of galaxies or the universe. Meanwhile, MOND explained those galaxies quite well, again, not perfectly, but better. MOND simply proposed that our familiar gravitational pull changes when it becomes very, very weak. Stars orbiting galaxies, for example, experience such a slight gravitational pull that it takes them hundreds of millions of years to do a single orbit hundred of thousands of light years long. MOND proposes a formula, therefore, that transitions from Newtonian to Mondian gravity as gravity becomes weaker. Mondian gravity behaves quite differently from Newtonian. In the case of a spiral galaxy, gravitational pull becomes nearly constant with distance, so that galaxies rotate much more like a bicycle tire spins than a solar system rotates. MOND was a modification of dynamics, so it could also be interpreted as a change in how objects experience inertia, but most people interpreted it as modification of gravity. This is called AQUAL, which stands for a quadratic Lagrangian, a kind of mathematical language for talking about forces and dynamics. Expanding on AQUAL are a few relativistic versions that try to account for how light appears to bend around galaxies as if they contain a great deal of dark matter. Until recently, MOND has managed to survive most attacks. In 2006, when gravitational lensing of the bullet cluster appeared to be a smoking gun for dark matter, people declared MOND dead. And while these objections were not satisfactorily put to rest, some counter-arguments, including that the bullet cluster didn't fit with the prevailing cosmology either, were made that allowed MOND to continue as a viable alternative to dark matter. When CMB data suggested yet another smoking gun for dark matter, researchers were able to reproduce the main features of the CMB with MOND. The key, many researchers determined, to resolving the stalemate between dark matter and MOND is to look at smaller and smaller scales. Recent observations of what are called wide binary systems, which are star systems where two stars orbit one another at a far distance, suggest either that MOND is ruled out, is more likely, or that the data is inconclusive depending on which data sets you use. We should be used to this by now. What about in the solar system itself? MOND was developed specifically so that its effects would not affect the predicted orbits of the planets, but nevertheless, MOND does not simply shut off when accelerations are high. Rather, its influence becomes less. Its influence is so small that, until recently, we did not have accurate enough positions for the orbits of the planets to make any conclusive statements about MOND within the solar system. Until now. The Cassini probe, which was launched to Saturn back in 1996, provided exceptionally good data on the orbit of Saturn for many years, and we can use that data to show whether MOND has any influence on that orbit as it is predicted to. The data suggests that there is absolutely no deviation from Newtonian gravity within the solar system. This complete absence of Mondian physics within the solar system appears to be incompatible with versions of MOND that fit well with the rotational rates of galaxies. In other words, you can't have a MOND that explains galaxies and doesn't appear at all within our solar system. In order for a MOND-like theory to be correct and apply to galaxies, it would not only need to change how gravity behaves at certain accelerations, it would also need to only apply to objects of a certain size, galaxies but not solar systems. While MOND doesn't have such a scale, modified gravity, MOG does, which means that that theory at least is still standing. And it might be a more promising direction for my next paper on 5D gravity. MOG and MOND are not equivalent. MOG is far more complex, but MOG has the benefit of having a relativistic representation with a scalar tensor vector representation similar to the tensor vector scalar theory. The Yukawa force is repulsive, which means it actually counteracts the gravitational force at short scales, while at long scales it disappears. At the galactic and larger scales where dark matter appears to play a major role, therefore, gravity is stronger than Newtonian. MOG can make it appear as if matter is in places it is not. That is a critical piece for explaining galaxy clusters where the bending of light makes it very clear that the gravity is not in the same place as the luminous matter, not simply stronger or weaker. MOG can account for the weak lensing in colliding clusters, including the bullet cluster and ordinary clusters. Before they collide, the lensing is centrally located, while after collision, the lensing moves away from the center because of the uneven distribution of matter. So far, MOG can account for the bullet cluster without any dark matter at all, something MOND has failed to achieve. It also addresses cosmology without dark matter as well. The main drawback to MOG is that it is so nonlinear and complex that it is extremely hard to model. Thank you so much for watching. Hope you enjoyed. See you soon in the next video. Until then, good night.